So I guess it's time. Yeah. Okay, let's get started. So this is about runtime PM and ACPI power domains. In particular, it's about device power management, device idle power management to be correct. And how this fits into the world of ACPI. And before I start talking about ACPI specific parts, I thought I'd give a quick recap of what I mean with a runtime PM centric path. And the goal we have with a runtime PM centric path when we invented that a couple of years ago, it's to solve a quite common problem that we have in the Linux kernel during system suspend and resume of devices, that we are very often waking them up and powering them on when it's not needed. So that obviously takes time, but it also means some waste of power, of course. The other thing that we wanted to solve was that we saw that it was quite complicated to deal with system sleeping drivers while you combine these two, runtime PM and system sleep deployment. So we wanted to make that more easy for drivers, and yeah, at the same time achieve the goal of getting a more optimized path. So in the end, we wanted to simplify the upstreaming of the ARM SOC PM code, and I think we have reached the point where we actually can see the results of this being deployed. So what happens was that we more or less saw that runtime suspend and system suspend operations was more or less similar, and that enables us to thought that we could reuse these callbacks for the same operations. And taking that into account, we also wanted to of course, fix the real problem of avoiding waking up devices when they are not needed. So this is more what we ended up with, and the nice part with this is, as you see, is the system sleep support in this driver is 2 lines of code, and this is quite common deployment actually. So what you have to do here for this particular driver is that you are deploying the runtime PM support, and you have, in this particular case, you have you have runtime PM callbacks in the driver, and
trying to show it, or not?
oh,
It sounds like you're trying to show us code.
sorry. Oh, that makes sense. Okay, so I was here. Yeah, the rest is not that important. So this is the this is the simple case I'm talking about. Sorry. So yeah, again, this is a driver, and you have the runtime suspend resume callbacks, which you set up with this set runtime PM ops macro, and that's a very common thing you do. But the important part here is the system sleep support. It's the set system sleep PM ops, which takes advantages of this PM runtime for suspend resume helpers, and that's kind of the whole thing about the runtime PM centric approach. It's about using these helpers to deploy sleep support. So this is a very simple case where you actually add 2 lines of code. So obviously there is some cases that are not as easy as the one we just saw, and to handle those kind of more tricky cases, you can actually have a flexibility built in there. You can use these helper functions from whatever suspend phase you want, so the no IRQ and late and whatever you want. And to deal with additional operations, like you might have some wake-ups that you need to configure when you go into system sleep. You can do that in your own set of callbacks, but from those callbacks actually call these helpers, and that takes care of all the corner cases that you get when you combine these two frameworks. So, yeah, one more thing, that if you want to have some examples, there is actually around 60 deployment currently in the kernel. So that's what I meant before. This has taken off since way back, and the deployment is increasing, and it's really nice that we can see this, both from a consolidation point of view, but also from optimization point of view, of course. So moving into the ACPI specific parts, when you want to make use of this runtime PM centric path from a driver, it actually puts some minor constraints on the so-called middle layers, and the middle layers is what we call in Linux kernel buses and PM domains, so to say, because this callback that we have for device power management exists on all these kind of levels. So if a driver decides to call this helper function that I was talking about earlier, that means that the upper layer will be called. So it's a bit tricky, but it's not that hard actually. And for most simple cases, like the platform bus, like the AMBA bus, or in these cases, the thing that is needed on this middle layer is actually nothing, because all it has to do is to trust that the driver deals with putting the device into low power state when it's needed. So more or less just calling the lower layer callbacks during sleep. However, there is cases where this becomes more tricky and not as trivial. And GMPD is not one of those generic power main. It's not one of those cases, but we needed to do minor adaptations. And those of you that might be familiar with GMPD, so when you have a device going into runtime suspend, we actually have like a governor up there, which is taking into account some latency constraints before it actually allows the device to go into runtime suspend. But you don't want to do that during system suspend, because then you actually want to make sure the device gets into low power state. So that kind of little knob you have there in the runtime PM callbacks in the upper layer, saying that don't do this when the sleep path is being executed. Very simple. It's just a couple of lines of code. Now I was thinking that, okay, that we have a bunch of other middle layers that is not as trivial. So ACPI, what can we do there, and why do we want to make changes there? Well, obviously the main reason is that I want to make sure that the ACPI can take the benefit from using the runtime PM centric path, of course, and because it's used by ARM, of course. But there is also another thing that's easy to forget here, is that we have these cross-sock drivers, and this is, those puts the complexity on a different level. So I have an example. It's an I2C driver that is being used on x86, and it's being used on ARM. And in some cases, it has this device that is managing may have the ACPI PM domain attached. In some cases, may have the generic PM domain attached. Sometimes it doesn't have any PM domain attached. And instead of trying to keep this, the driver being aware of all this kind of trickiness, you may think that there's nothing that you need to take care of in the driver, but actually there is. So I looked into this I2C driver, and I found that this was completely mess. It hasn't been working for ARMs since several years, but it's been working for Intel. So I was trying to make it work for ARM, but then I managed to screw up Intel. So yeah, so I realized we need to do something about this. And that's why I started to try to make the ACPI PM domain aware of the runtime PM-centric path So to understand what we actually needed to do, you should think about the ACPI PM domain when you compare it about the generic PM domain, is that ACPI PM domain is actually maintaining, is actually dealing with powering on and off of the devices on the PM domain level. While in the generic PM domain case, the NPD is only taking care of the shared resources, like the power rails and the clock domain. Then it defers or relies on the lower level drivers to actually powering on off the actual device. You know, clock gating, pin control, all that stuff that goes on the lower layers. Because of that, the PM core maintainer, Raphael, decided some time back that he also knew about this common problem about waking up devices when it's not needed. So he tried to invent something that was suited well for ACPI. And he came up with this so-called direct complete path. So yeah, another way of dealing with the similar problems. However, this direct complete path has limitations, and limitation that is taken care of in the runtime PM-centric path. But that may not be the most critical thing, because the other thing that I really don't like with it is it's damn complicated. And it's not just damn complicated in a centralized place, but it's also spread it out to drivers. So it's not very easy to support. So that made me go into the ACPI PM domain. I started to take a stab on what we need to do to make this work. And more or less it consisted with three parts. First of all, I wanted to make the runtime PM callbacks in the ACPI PM domain aware of that they may be called during system sleep. Second, I wanted to make sure that in the system sleep path, you don't want the domain to power on or off the devices, but instead just trust the drivers to do the right thing. And the third thing was that I wanted to prove this behavior. So I took this I2C driver and showed that how the code ended up being 2 lines of code, as I showed before. So I'm more or less removing 30, 40 lines of code in the driver, and 2 lines of code was all that was needed to get an optimized behavior. And yeah, so moving the complexity a little bit up in the ACPI PM domain instead. But yeah, it got rejected after a couple of iterations addressing the concern that Raphael pointed out. In the end, he didn't really like the approach. He wanted to make it a bit slightly different way. So we were at Linux Plumbers a couple of days ago, and we discussed it over there. So yeah, we concluded on some of the next step we wanted to take. But I think more importantly, we also concluded that the direct complete class that Raphael invented a while ago isn't good enough. It's too complex and it doesn't really do the job very well. However, it's already there, so it might be a little bit tricky to remove it. But yeah, in the end, we want something that is better than that. And exactly how we are going to deploy the so-called runtime PM-centric part is still open, so to say. But yeah, we have Raphael on board, and he likes the fundamental idea, what we wanted to do, but we're not really agreed on how to reach the point of actually implementing it. We also concluded that I pointed out this I2C design driver as an example, but this is just one case. It will be worse. Definitely, we will have more cases where we will see this complexity grow, and I think it's better to deal with it now before it gets too complicated. So yeah, that's where we are right now, and until we have a complete solution, we will have to live with a non-optimized behavior for these cross-sock drivers and for ACPI devices and PM domain. But we're working on it, and we'll keep you updated. That's actually it. And do you have any questions? Feel free to ask. from spec level point of view? ACPI? So I think ACPI already has the, yeah, there's nothing that you need to add in the spec to support this. So this is already there. It's just a matter of dealing it with a slightly different way in the software than we do today.
If that changes.
Well,
If that changes.
yeah. So one thing that I struggled with a little bit when I was working with this was that I needed to have x86 hardware to test the stuff for ACPI, and I was talking to Lorenzo at Linux Plumbers about getting some hardware that we could test this on ARM SoCs, because that would be a lot more fun. So yeah, if you know about some hardware that we could use to test it, it would be good.
The new one, the new computer that has been released during the keynote, the release.
It's
Oh.
a number of different specs for its.
Oh.
The truth is, the gig. There's a lot of work to be done.
Mm.
Yeah, a lot of expensive.
Mm.
There's also not much hardware to describe an ACPI.
That-
It's very simple stuff.
Yeah.
So there's not actually much you can describe an ACPI.
Yeah. We'll see, but it would be great to have some ARM SoC to test it.
To be fair, platforms that are enterprise grade that can be the ones that carry ACPI. For us in ARM, it's just hard to get them. In fact, harder than some computers. Most of the vendors are architectural SoCs and therefore they're in direct competition with us, like Bob, Carrier,
Okay.
It's kind of harder for us. It's easier for the ARM to get that hardware.
Okay.
I mean, obviously, it seems like Juno is a network.
Mm.
Juno is something for the same simplicity issues.
Yeah, we will have to see. Okay. No more questions? Thank you for listening.